Awesome. As people file in here, greetings to everybody. This is discussion number 80, April 27th, 2023. Here to talk about all of these quantum machine learning platforms. So they've been around for a couple of years, and I would say they're getting more attention. And feel free to unmute or come on as you come on in even recent months. So Google has this thing called QSIM, and it's doing better than Circ. And in general, the first question I wanted to ask here is basically this: how does classical machine learning struggle with input data, like by volume, by type, those types of things? And it's basically, there's reasons why there's all this quantum machine learning out there. We're talking about Google's TensorFlow Quantum, MIT's TorchQuantum, that it serves a specific purpose. So a lot of times it's not going to replace everything classical. It's more for a supplement to it. So helps with a quantum convolutional neural net in the specifics behind it. Why does it make sense to run a quantum circuit here? So any feedback as far as that first question, so how does a classical machine learning struggle with input data? What are the assumptions? Basically, what's traditionally fed with it? What would you like to feed with it? How are we limited by, training sets, those types of things that limits testing results? So feel free to come on. So you can unmute or, come on with video too. And, this is meant to be a fireside chat. So I'm assuming a lot of the people attending right now have a fair amount of experience with machine learning, either with TensorFlow or with PyTorch. So those are the classical equivalents to it all. And I'm just kind of interested and kind of get some feelers out there as far as, the number of people actually already doing quantum, want to get into quantum, or want to go further with quantum. So you should be able to unmute, and start video as well. And we're going to have more people coming on here. So as you can see, it should be pretty busy. But basically, I'll tell you this is that, even if you don't have much machine learning experience, you can get into quantum machine learning. It helps to learn some of the physics behind it for sure. And, there's specific areas where it's excelling in where you don't need an awesome quantum computer in. So this would be something like, image analysis. So they're using standard convolutional neural nets in addition to a quantum circuit to improve classification accuracy, decrease loss, those types of things. So let's see. And feel free to put in the chat as well. So the chat is definitely open here too, as far as kind of where you're starting with this. Now, there's a number of these. So there's Google TensorFlow, MIT TorchQuantum, Qiskit, which is IBM's machine learning. You have Xanadu's machine learning as well. You also have, the Xanadu penny lanes, and then you have Azure. So this is Microsoft. There's Paddle Quantum. There's VQNet 2.0. And I'll tell you this is sometimes it's just a matter of preference as far as like what your specific gates look like. So are the gates, do they tend to spell out, each individual gate in a circuit? And so with these types of things. So, and again, so we have a number of people here that have been on before. And like I said, you should be able to come on with chat. You can come on with video as well. And then, so we do have a couple questions here. Actually, it's a comment. So Ron Schreiner, who's been on before, he says Google TensorFlow Quantum, MIT TorchQuantum. And his favorite machine learning book with this is Hands-on Machine Learning with Scikit-learn. So for those that don't know, and then so this is Keras and TensorFlow, concepts, tools, and techniques to build intelligent systems. So machine learning is a fairly, and deep learning too, are, definitely have been around for a while. And then, so my assumption is there's a fair number of people that think that we need an awesome quantum computer to do anything. In reality, you can use quantum simulators for certain tasks, not everything. But the big benefit with that is that they're noise free. So that means that quantum computers are going to have noise for a while, like the real hardware. So, on all these different manufacturers, basically. So, that's the thing with that. But basically, programmers are designing software based on, using smaller quantum circuits that don't take up a lot of time, like a bigger quantum circuit would with a quantum simulator, in lieu of, just, waiting for awesome quantum and trying to get results now. And in literature, it's happening. So that's a cool thing there. And then feel free, so you can come on, or you could put it in the chat as well. And the other point with this is a lot of this is just being built on existing classical frameworks, the TensorFlow and PyTorch. So it's basically, a lot of these things is that you're keeping that. So you're keeping that knowledge that you have from those other libraries. And in this time, you're, for specific parts of it, you're using a quantum circuit. So that's, that's basically the big thing there is, where it makes sense to do quantum mechanics, definitely. So I have another question here. So in what cases does machine learning take too long, right? So are you training on too many images? Is it a problem with the hardware? Or is the CPU too slow? Those types of things. So feel free to put in the chat, or you can come on as well with that. And there was, the big things that come to mind as far as the evolution in machine learning and deep learning. Well, it's first deep learning. And the second thing is obviously GPU support. So actually, when you go to run in these Jupyter labs, a lot of the time, it'll actually, ask you, it'll pop out an error, like, are you running GPUs? And you just hit run again, it goes away. But it's a fairly common thing to run on, say, faster GPUs that tend to be a little less accurate than CPUs. And now we're going into quantum with quantum simulators and real quantum hardware, those types of things as well. And would anybody like to share as far as like their specific, experiences with machine learning and especially deep learning? Deep learning being, I think it's 3 or greater hidden layers is kind of that qualification. And kind of what brought you here today as far as like, are you learning to, are you desiring to learn more about quantum or speed up a specific task? And the solution may be available. It's a very specific thing. It depends on your application, with these things. So it's definitely some fields, like if you do simulations of caffeine molecules in the human body, all inside of a computer, and you're not getting that, it's going to take likely millions of qubits to get to that point of simulating every atom of, I think caffeine's 24 atoms to get to that point. So other things like image processing seems to be off to a great start. And again, these are smaller, they're called quantum bits or qubits. So 4 qubit circuits run with an existing deep learning neural net, such as like an AlexNet or ResNet, these types of things. So, yeah, so there's, and I think Ron kind of like pinned the head on the hammer here, is basically another great book, Designing Machine Learning Systems, an Iterative Process for Production-Ready Applications. And I think a lot of this stuff, I was just watching an MIT video on, the quantum aspect of this and kind of how it's like, looks like it's taking after kind of the success with machine learning, is that some of it is just down to a science, so like if you do X and you do Y, you expect it to do Z. So there, in like it with quantum too, is that there's that, theoretical approach, and then you also have, the practical use of it too, and they kind of like feed off of each other for sure. And okay, so we have another comment here. I'm a medical scientist by training, currently studying data science and gaining hands-on, okay, using classical MLD. Okay, I am becoming interestingly more curious about quantum computing and quantum ML and its applications in data science in general, and primarily, this is in the chat, and more particularly in the biomed field. So Antiguo, I would definitely suggest getting a free IBM Qiskit account. So it's QISKIT. And then so with this, you basically are, free access to quantum simulators, free access to a lot of these things. So should be able to come on here. Is somebody, okay.
Hey, Kevin. Sorry for the delay. It was, if we could go back to your initial question and try to define some sort of scope for it, like what problems are people having with input data in classical machine learning? Is there a specific domain that you're interested in, or are you just looking for a list of all issues with that step in the process?
Well, it's really up to you, but I was, I've come from medical images, so I just think, like, is it a 2D image? Is it a 3D image? Is it the screen resolution? Does it have to be drastically reduced before you can do anything with it? So you can answer it how you like, Ron.
Well, I think most of the issues with classical machine learning just have to do with volume, either sets of targets or data acquisition. Data can, if you got data that you're collecting from a whole bunch of different sources, there has to be a step in the process to funnel those down so that they all get listed in the same format. There's all kinds of issues with data normalization. There's issues with finding or creating training sets that have inputs and solutions so that you can train with if you're going to do supervised training. Lots of issues with converting. Once you have those, you have to convert them into data formats that are machine learning conducive, and that a lot of times that isn't what's involved. There is you're moving anything that's got like a scalar value, you're remapping it so that it's either between 0 and 1 or between -1 and 1. These are the number ranges that neural nets tend to like better than just drastically different number scales. But I'm sure I'm just scratching the surface of the issues with classical. And I guess one thing we could, you could pick out is we're talking about a production environment versus a research environment. The issues are going to be different also.
Yeah, that's a really good answer. And I've already come across some of those as far as, I'll get to training, and then this is even with a classical neural net. And then at the end, there's some error, and then it's backtracking through all these additional cells. So yeah, appreciate that. Anybody else? So this could be, kind of your experience with it. And it doesn't have to be this. These are just to kind of spark the imagination. Now, the second one was, in what cases does machine learning just take too long? So is it just known that this isn't a good experiment to run, just because, history shows, and we know it's either going to take too long, be too expensive, or we don't even have the resources to run, from the beginning. And I definitely see some new people come on. So, you could either post in the chat, or you could unmute or come on with video. The whole point of this is basically this, is that, TensorFlow Quantum, there's an individual, his name's Owen Lockwood, and as of 3 years ago, he's been posting on GitHub and answering questions, and basically when people can't run specific code. And I posted this in the comments of the on the LinkedIn, and basically he continues to help. And there's so many known issues just with any big language. And that he says for this out of 700 whatever known issues, and trying to work through that all. Now, I had mentioned Qiskit, and then we have PennyLane too. So there's Xanadu PennyLane. So this is quantum machine learning. And I would say it's probably the easiest to get started, just because the tutorials are relatively straightforward. And the other ones, TensorFlow Quantum may be the biggest of the bunch for machine learning, just because it's built on the Google success of TensorFlow. And the PyTorch, and now we have TorchQuantum. That seems like it's a lot more specific, like it's for the advanced experts. And they published some papers on MIT's is the Hand Lab, and I've actually seen some of those. So I've read through some of those. So I think that's more for the custom tailor-made. But all of this will be getting bigger, because quantum simulators are getting bigger. We still have the promise of NSF's practical quantum computer for this year. There's an ion trap manufacturing quantum computer facility going in first half of next year, 2024. And the government's 110% behind quantum. And in fact, quantum is a government initiative. So I guess for everybody today, I would definitely hop on so you can run real quantum computers for free. So this is IBM Qiskit, Qiskit, and then it's called their circuit circuit composer, IBM Circuit Composer, and you drag and drop quantum gates. Now, I guess, and if anybody has any questions, feel free to hop in. But the basis of all of this, so in classical world, you have transistors and they're physical gates. Now in the quantum world, we have gates, but they're matrix-based. So they're essentially software. And you can combine these and optimize these within circuits to get better results. But it's just, there's no way around. If you really want to get into quantum programming, you have to take the tutorials. You'll have to take look at all the YouTube videos, not every single one, and kind of spread it out between MIT, IBM, PennyLane, and shoot for the small wins. Design quantum algorithms that are less susceptible to quantum noise. Put together circuits either in Qiskit or you can do PennyLane tutorials as well. So I think I have it pretty accurate when I say that, is people are either coming in because they want to make that transition from classical or quantum, or they just want to experiment with quantum. They think it's awesome, and more power to you. And it just takes time. It took time to learn Python, and it took time to be proficient in navigating Jupyter Labs or Jupyter notebooks, those types of things. So with QML, probably the one that's most documented for quantum machine learning, I don't think it's Qiskit. I think it's actually the TensorFlow Quantum. So this paper came out, it's an archive. And so it's ARXIV. And I'm like 15 pages out of 50 in it. And it tells you exactly what you're doing and why you're doing it in order to give better results in quantum machine learning in specific. So with that, anybody have questions or kind of comments on this? Because a lot of this thing, you just read little bits and pieces in the news with that, and it's not inherently clear as far as what direction you should take in implementing quantum circuits, quantum simulators in your workflows. And, basically what's your next steps with that? So I created this list, and it's basically as quantum on the left, classical on the right. And then I've talked about a lot of the stuff, the available libraries or platforms in quantum, that already exists. None of this has gotten huge yet because the actual hardware is still emerging, and so are, quantum simulators. And, there's, like with anything, it's an art. So when you're designing, so a quantum circuit contains a quantum algorithm, and then you can make modifications to that algorithm to get, if you're looking for better accuracy, lower loss, better image quality. It just depends on what your task is. So, for instance, I was just watching an MIT, video, and they call these super circuits. So, a super circuit is basically the top circuit that the sub circuits are based off of. Now, just how you can iterate. So, when you're training in quantum computing, you're essentially training the parameter numbers. So they can be like pi over 2, pi over 4, or any other combination of negative or positive, typically between maybe 1 or 4 with these. So you'll see in research papers is that after the training, sometimes they'll give you those. So that's the circuit is trained, and that's the exact configuration that will give the whole entire circuit, or the whole entire model, the best results. So what IBM or what MIT does is basically they do that, but with the circuit. So they'll keep plugging in, and there's more detail with this too, but basically supplementing different quantum circuits in to see what will give you the best results. Now, quantum algorithm is inside that quantum circuit, and the circuit is more like the framework for the algorithm, but they're oftentimes used synonymously, that same type of thing. So, they talk about pruning. So say, for instance, if there's a certain rotational gate that has a value really close to 0, you can just prune it. So meaning that you could just throw that quantum gate or matrix out, and then it'll be better off without it than with it, those types of things. And, you really just have to get on and start running. So I get the sense that maybe this isn't, like, for most of us, something that we do every single day, although I'm, researching and studying in that direction. And on a IBM Qiskit, so design your own algorithms or learn from an MIT paper, and actually run exactly what they publish. It's a quite rewarding feeling. So you're literally just clicks away from running on a real quantum computer or running on a simulator, and it's meant to be that way. And like I said, most of this is just free of charge. So IBM has put billions of dollars in this, and the industry as a whole too. It's taken basically a lot longer than many people have thought. Going back to maybe 2017, and even before that too, to have a less noisy quantum computer. But you as a researcher, there's no reason not to go into it. It is a huge time commitment. I guarantee you that. But I and probably other people in the chat here would agree that this is something worthwhile, right? To improve other classical circuits. So, and then, so there's a comment in the chat. So there's all these good quantum resources too. So why not shoot for the ones that are free first? And some of these are just low cost anyway. So maybe 40, 50 bucks. And, so there's definitely some suggestions in the chat here too, cover to cover, reading. I'm a huge audio person, but, it just depends. So speech to text, text to speech. So there's a lot of resources. So you can't mention that without mentioning Qiskit. So Qiskit is just one of these phenomenal free services out there. And I probably run over 100, quantum circuits on their real quantum computers. And then for sure, their simulators too. You oftentimes use simulators when you're not even aware of it. So you can specify which one you want to use too. So do we have anything like testimonials, as far as like, okay, I started my career with machine learning here, and then now here I am, April 2023, and I'm here with machine learning, but I would like to do that. And then maybe some of us here could kind of field those comments too, and, say exactly, oh, you're better off using, programming here with IBM or Penny Lane, or even, TorchQuantum or TensorFlow Quantum. Go ahead, Ron. Did you have something?
I was just going to say, I wanted to reinforce your statement for the people asking about how do you get started in quantum. Short of finding a university that has a course, which is very difficult because most of them tend to be postgraduate, do what Kevin said. Go to find the IBM Quantum Experience, sign up for a free account, jump in and start hacking away, start following the examples. Qiskit, there's a Qiskit site, which Qiskit is owned and probably owned and operated by IBM, I'm sure. There's the Qiskit textbook that you can just go through and do a pretty good job. If you're a book person, all of those books I dropped in, the first list of books that I've read cover to cover, I would recommend pretty much any one of them if you have specific questions. They're not all the same. If you're just curious and you want an introduction to quantum and you don't want to spend time online, the Quantum Computing for Everyone by Chris Bernhardt is an excellent book. It's well written. It's a fast read. It gives you just enough math to get through the beginning phases of understanding principles of quantum and qubits. He tells you right up front, we're not going to spend a lot of time on complex numbers, and you don't really need to. Now, this will not be the only book you can read on quantum and be productive. It's a good start, gets you a good foundation. He brings in complex numbers a little bit towards the end, but more importantly, he does introduce the concept of Dirac notation, which is all over quantum computing. Just gets your foot in there, gets you into a place where you can put your head around stuff. There are some, low-level examples of quantum algorithms and stuff, but again, it's an introductory book. You should go through it pretty quick. It's well written. There's not a lot of there's really no heavy math in it. It's a basic introduction, basic entry into linear algebra. Some of the other books on there, if anybody has any questions about them, I can tell you what my experiences was with them, and you can pick one. The current book I'm reading is really, and that's the one by Jack Kadari. This is really a college textbook, so it is full of math, and might be one of the downstream books that you go after. I mean, if you're already in the postgraduate position, give that book a try. It's if you've got a math background, if you get some physics background, you might not have any issue with it whatsoever.
Yeah, that's awesome. I would just say, like, of all the ones I've basically modified, improved, supplemented for different quantum algorithms, there's a penny lane one called convolutional neural networks, and it highlights stuff, right? So it tells you exactly what's the size of your training set do you want, and then you can change it they start at 50, and you can go up to over 100. And it's very straightforward. And if you know anything about hyperparameters, I will give you this hint. I haven't had too much luck as far as them publishing models and changing atom optimization and loss functions. They're typically already optimized. The ones that I've seen so far is like 3, 4, 5, something like that. And I would definitely, if you want to hop straight into quantum machine learning, you're at the bare minimum, pop open the Qiskit page where it says single qubit, 2 qubit, or 3 qubit quantum gates. So again, these quantum gates are matrices, right? And they're on your screen. It's an H gate is a Hadamard gate, which is a 2x2 matrix. And then you can have like a Toffoli gate, which I think is a 3 qubit gate, meaning 3 quantum bits. You have 2 controls and then 1 target. So I would say to be successful in quantum machine learning, you need to also know the circuit layout. So on the left, you typically have resets, and then the wires, which are horizontal, represent each of the quantum bits. Now on the right side, you're going to have measurements. So every quantum computing operation that's run needs to be measured, and that's done with a classical computer. So that'll get you going, know the gates, know the circuit design, and then that way you can make changes. Say if there's a March TensorFlow Quantum, model that I ran pretty quickly, and it ran pretty well. So the more you know, the more you can change as far as the algorithm or the hyperparameters or these types of things. But I think Qiskit, many people start off learning, and I'll likely keep going back. But say, for instance, for machine learning, I haven't seen a great amount, like TensorFlow Quantum is specifically for quantum machine learning. Same thing with TorchQuantum, quantum machine learning. So yeah, it's just like, spark your imagination for quantum computing. And then you'll have to learn some of those basics, but not everything, if you want to get going with QML and then, quantum neural nets and those types of things too. So there's a question in chat. What prompted to get into it? I was fascinated by this. Basically, this is maybe 2018, 2019. And I was actually applying for a job at that time. And I said, what about quantum computing? And the manager, the president of the company says, we don't do that. So, it's a slow transition because we didn't have quantum supremacy until October 2019. And then AWS Briquette didn't get started till December 2019. And then we had their first $1 billion IPO called IonQ in October 21. And I saw all this, and I kind of had a block as far as programming and coding, because I took one course at the university, and I was taking other courses, and it just didn't click. So I convinced myself I just have to learn how to code. So I go to many Python groups, such as like Meetup or, even LinkedIn. And then I just start, picking up all of that as far as the AI, ML, and quantum. It'll continue to post out hype, and you'll find yourself in a better spot if you get super into one thing, become that expert, have a portfolio, and then all of a sudden, many people look up to you. So I would shoot for that as opposed to like the general stuff. Although it's nice to mingle, with other important people in quantum. But that's the limiting factor is, do people really need you? And that's the business world. It's hard and it's tough. But if you have a whole university that wants to get into quantum and you're the only one that can program in TensorFlow Quantum and Qiskit and all that type of stuff, that to me, that has greater value. Any other questions or comments? I know a lot of people are still coming from many different areas, and keep in mind, QML and quantum neural networks is not mainstream yet. The quantum computers, like say for medical, the actual physical quantum computers that are emerging right now that are kind of noisy, it may be a while until they're accepted in medical and, regulatory passed and all that kind of stuff. Now for quantum simulators, so you can simulate quantum mechanics, meaning a quantum algorithm and a quantum circuit inside a CPU or GPUs. And in recent weeks, there's been announcements with GPU quantum simulators by NVIDIA, or maybe recent months. It's just been unfolding. And what it's really good at is it's just noise-free. I mean, as noise-free as our iPhones are, compared to quantum computers, a lot less noisy. So figure with a quantum GPU simulator, you're looking at faster, but maybe more, less accurate results. And then with the CPU quantum simulator, you're maybe looking at slower and more accurate results. So there's all these tricks because the whole industry has been thinking, the quantum computer is ready. Now the ion trap technology, and Ron could talk on this too, has been, probably above the other ones as far as like the technology, it being suitable for different areas of research. I've seen it in multiple Nature papers. So Nature, like nature.com kind of thing. So it depends on the application, but in general, the more noise that you have is also associated with other detriments like barren plateaus and more quantum bits, with real quantum computers too. So quantum simulators, I haven't seen much over 40 quantum bits because it takes a lot of RAM, basically classical RAM, to do a quantum simulator. So I haven't seen too much more than that. And for small quantum circuits, like the one I been saying for image analysis, it seems to be fine. But for other things like simulating molecules, you're not even in the same ballpark. You know, you're talking like probably tens of thousands of qubits and if not millions to do what you're trying to do. But then that area, they'll approximate things, you know, so they'll flatten a 3D molecule into 2D. And it's just trying to get stuff to work. If you read many of these papers, like, why did they do this? Okay, well, it's to get it to work. So, and feel free, and you can come on if there's something, you know, even basic stuff about quantum, you know, is fine to discuss. But that's my assumption, basically, is everybody that's coming today wants to use quantum machine learning. And like I said, you don't have to know everything about quantum physics and even, you know, some of the other basics about, well, I shouldn't say that. You should be familiar watching YouTube videos. You know, there's single qubit gates, double qubit gates, like that's the premise. So typically, if you want to get better results, it's because you made some modifications to the algorithm, or you made some hyperparameter modifications within the quantum algorithm, or you did, you know, your classical hyperparameters, you know, changes with optimizers and loss functions that you're probably familiar with. So, you know, it's just, you know, you have to ask yourself, what are you trying to do? Is quantum machine learning the best thing? And then the big thing with all this is the type of data. So most data is, most data today we have is exponential. Like we have an exponential amount of classical data. So this is images or, you know, stock prices. They're integers, strings, or floats, you know, so that's classical data. So to do stuff with that, you have to convert it into quantum data. So that's done with, say, like a feature map. And then you have a quantum circuit, which has the quantum algorithm, and it's doing stuff with that quantum data. And after it's done with that, it goes back into classical data. And you'll hear this from anywhere from cybersecurity to other fields of, you know, post-quantum cryptography. And to get the maximum benefit is to start off with quantum data, such as like chemical simulations, but that has its own issues because it's requiring tens of thousands of qubits to do it, you know, to a full effect. But you'll get far when you're looking at notebooks if you can determine what part of the notebook is classical data and what part, you know, it's getting turned into quantum data, and then, you know, that kind of stuff, like tracking basically the progress of your notebook. So see, some new people came on, and again, feel free to put in the chat too. And this is, you know, basically, if you don't have much coding experience at all, you know, that's fine too. And, you know, there's no real question as long as it relates to, you know, quantum coding, or even Qiskit is based on Python, if you're familiar with Python. So this is IBM Qiskit. And I think at this point, there's been over 2 trillion quantum circuits run on quantum, a mixture of quantum simulators and real hardware. So it's a niche thing still, but the people that are running it, they're after something, right? Like you want, you know, less noise to be affecting your circuits, or you want, you know, your complete code to you know, have higher accuracy or less loss, those types of things too. And just show up in the right places. So right now, I know a lot about quantum, and then I'm learning a lot about quantum coding, and then I go to a lot of Python groups. So, and then, you know, Ron is offered in the chat here too, if you, you know, like to learn about Python or Bash. So you have to start somewhere. So, you know, like I said, if you could come on, or you could put in the chat too, to just kind of like give us give me an introduction, a story about yourself, those types of things. But, you know, and all these things, if you spend time in a certain area, you'll get there. It's just, you know, many people just give up along the journey just because it's different or it's new. but keep going to meetups, keep going to, coding meetups, and eventually you'll start to see that, like, oh, do you do quantum? And like your boss, maybe in a year or two, might say, like, do you have quantum programming skills? So it's not one of those things that's as common as like Python or Java or Bash and those types of things. And then, so Marilla, thanks for coming on. So she says she's a data scientist, joined for curiosity. Okay. And I would, the quick wins, right? So setting up your Qiskit account on IBM, and they didn't pay me to say that, but it's just, it has so many different tutorials, meaning like full notebooks that you're just clicking play. And then most of the times they work. If not, you might have to add like a JSON file. And it's just so easy. And you can do your own quantum circuits, and you can run on real quantum hardware, that type of stuff. But I would say, the basics, and there's a book by Worley, or his short for William Hurley. It's called Quantum Computing for Babies. And trust me, I've read it, and I needed to read it at that time. Is in the classical world, you have a bit, and your bit can be, like an on or off, kind of thing. Now in the quantum world, so that's 1 or 0. So in the quantum world, it could be superposition. So it could be 0 or 1, or anywhere in between this qubit sphere. It's called a block sphere. And then this specific bit can be entangled to another quantum bit at some distance. Actually, it says it can be infinitely far away. And what that allows you is for exponential processing power, more and more so as you get more quantum bits. So you can actually watch that video, or that's paraphrased from this Quantum Computing for Babies on YouTube, and it'll help you with that. The other thing it says is basically the reason why there's quantum computers is not because they're fully functional, because they're not, is because it's good at running specific problems, especially like quantum machine learning problems, really, really well. So increasing number of quantum bits, increasing kernel size in images, or, image processing. And there's mathematical advantages in quantum that instead of increasing time exponentially, like classical would, is in the quantum world, it's only logarithmic. So if you've heard of everything with Shor's algorithm, is basically, as you're increasing the factors or the keys, or, basically the security, cybersecurity, it's not shooting up like that. It's like this. It still goes up as far as the amount of time that's needed. And I would say, just there's quantum teleportation. So, and there's probably at least one other person here that could explain it too, but this weird world of quantum teleportation, and there's another analogous algorithm like that, where you can pass information from here to here, but there's no record in between. So I would say a good respect and a good love for quantum mechanics, quantum physics is a good entry point, right? Because like I said earlier, if you just look at gates, those types of things, it might just seem like learning something else, but it's really a whole brand new thing. So there's a question here. Have you been able to show customers a tangible benefit using a quantum neural network versus classical neural algorithm? So first off, most quantum neural networks are not deep, so they don't have many layers. So most of the ones, so there's advantages of running, say, like, it's called depth and width. So width is just like how you'd read a circuit. It goes, depth goes left to right, and then width goes up and down. So a deep circuit has more of that same gate or other gates kind of piled up going left to right. Now, width is the number of quantum bits. So a deep circuit goes up and down as you look at a quantum circuit. So, and somebody, if you want, you could post just a simple quantum circuit in the chat for people to see. So the tangible benefit, it depends on the application. So like I said, the image processing one that I've been, or image analysis one I've been describing is basically the bulk of the computational power is still performed by a classical neural network or like a convolutional neural network, like a ResNet or like a AlexNet that's common. And then the quantum circuit in that case is run on a simulator, and it's a shorter, maybe 4 quantum bit circuit that's of, say, of depth of 6 or something like that. And, you know, that's mostly how I see quantum neural networks or algorithms used, is that supplement of something that's much bigger processing wise on the classical end. So D-Wave, for instance, has interesting systems for reducing parameter space using. So yeah, I think D-Wave tries to catch it from the beginning. This feature, reducing numbers of features. So for those that don't know, D-Wave technology is called quantum annealing, and it's been proved to have benefit. It's just that it's only for optimization problems, or typically optimization, but this one I think is just for a specific part of the circuit. But yeah, I think by and large it's that. I don't think that quantum deep learning is quite a thing yet, which is what many classical neural nets are, just because, you know, the CPUs and the GPUs. But if we simulate on a quantum, you know, simulate quantum mechanics on a CPU or GPU, things tend to get a little slow, and then, you know, you can't do everything with it. Like, say, for instance, like a quantum computer with less noise in 5 years, those types of things. I appreciate that. Yeah, optimization. So, and you can, you know, feel free to ask any questions. So this is basically, you're going to be learning, you know, if you want to get that competitive edge or competitive advantage over, you know, classical coworkers, those types of things. Because I'll tell you the truth is, many organizations, they won't fully adopt quantum until it becomes non-nascent, or becoming, you know, basically it's more mainstream. But you'd find it hard to argue against this, that IBM Qiskit and, you know, Quantinuum, Honeywell, and, you know, TensorFlow Quantum and, you know, TorchQuantum, they definitely have a head start, right? And especially like for simulators right now, those types of things. Right, and so costs, so there's a comment, so basically it has to become financially, you know, viable, you know, with all these things. So so what's going on with quantum computers is this. So you have simulators, which are run on either CPUs or GPUs. And I think that's most of the experiments being run, just because they don't have noise, but they're limited in the number of qubits, and, you know, the algorithm size, they're limited in, you know, circuit size. And that's probably going to be the case, right? Because I think for 40 quantum bits, it's something like an exabyte of RAM, you know, classical RAM that's needed. Now, on the quantum, like the real hardware side, you know, that's basically, they're all in the cloud. I don't have one here, you know, I'm on a laptop. It's, you know, CPU, GPU, whatever. And say, for instance, like AWS Braket, they have, I think it's 5 different manufacturers across 3 different types of hardware technologies. So you might have gate-based superconducting qubit, you might have, or you do, and then you have, I don't even think they have quantum annealing anymore, but photonics, and I think they have neutral atom. So an optimist view is that there's 4 or 5 at least types of hardware technologies for real quantum computers, and any one of them can break through at any time. I think the one that might have the greatest potential is spin qubits, because you can do semiconductor quantum computers right on the same line as you were just designing chips, I think with some modifications, but you can. So that's all up in the cloud, and you pay per shot. So quantum computers are not deterministic, meaning that they don't output as 0 or 1, is that they're probabilistic. So your output might be, your first one might be 0, 0, 0, 0, depending how many qubits you have. And then the second one might be 0, 0, 0, 1. And then if you're running like 1,000 shots, and if you have noise, then not 1,000 of those shots will be in the 0001 state. It'll be in other states, those types of things. And that's a function of how much error the quantum computer has. So you can rent time through there. You could sign a contract with IonQ or Quantinium. I think it's the big ones are Google Cloud, Microsoft Azure, IBM Qiskit, those types of things too. So it just depends. You also get better results if you run 1,000 shots compared to 10,000 shots typically. But once you get up to 10,000 shot, if you take 10,000 times a penny, 10,000 times 0.01, it starts to get up there. So you'll see in research papers all the time where they'll cut off a run, towards the end because of the cost. And I've never seen 100,000 shots, and they vary based on hardware. So there's that. I know Microsoft Azure takes your credit card to begin with, and then IBM Qiskit, they've never asked for it until I upgrade to it doesn't make sense to run too much on a 100 qubit circuit, which they have. It's called 127, it's Eagle, but it doesn't make too much sense because it's like, you also have more error, with those higher qubit counts and those types of things. So the goal right now, and I think that a good direction to get started is focus on the specific tasks that people have already published on, make iterations to it as much as you can. So meaning most of the processing is done classically, and then do, side, quantum simulator on a GPU or CPU, those types of things. So, and yeah, go ahead, Ron.
So I saw a comment from Jim about he has machine learning customers, and he wants to keep an open mind apparently on when will quantum be a thing for QML or for machine learning. I think the important thing right now is it financially sound to use quantum. I always go back to the example that came from a presentation that was right here in Kevin's group of a team. I think they were out of India. They're using the D-Wave technology to optimize a machine learning program, basically to do better truck delivery routing. Okay, so what they claimed that they were getting was a whole 6% improvement in routing efficiency by using D-Waves. And I'm going to guess it could have been their 5,000 qubit annealer. Because I mean, it would take some qubits to do routing at that level, but they're claiming they were experiencing a 6% improvement, and you're like, oh my gosh, but how much money are they spending on D-Wave? But 6% for that particular business is a big deal. If you're a trucking company and you're spending just a ballpark round number, if you're spending $1 million a day on gasoline, you're going to be all over a 6% improvement. That's going to add up. So that's a situation where quantum machine learning is viable, and apparently those guys over there are having some success with it. So does that mean it's going to work for every business? It's going to have to. The performance increase is going to have to get better, and the cost is going to have to come down before it's more of a broadly accepted tactic.
Yeah, it's a great demonstration. There's still I think the quantum annealers are still refrigerator size. So a lot of this, you talk to the experts and they say that in some regards we're still in the 70s or 80s as far as that classical version of what's happening today with quantum. And I would say in some cases, but not with all. So it just depends on the application, the type of hardware, because the gate-based superconducting qubit, which is IBM, Google, Rigetti, and more, is theoretically the most powerful, but it's also the most susceptible to noise. So IBM has switched to a design called hexagonal. So it's like a six-piece layout, something like that, to cut down on error, even though it also cuts down on their performance. So out of everything, IBM's probably most invested, but I think that they're also allowing some of these other technologies to use Qiskit, and don't quote me on that. I just saw that kind of flash across the screen. So I think going to many of these quantum discussions, ion trap technologies is definitely the one to look out for. So this is a company called IonQ. So they IPO'd in October 21 for over $1 billion. And then you also have Honeywell, and their version is called Quantinium. And then they're part of this, Fortune 50 or Fortune 100 company, which is Honeywell. So I would say Quantinium might publish more, but IonQ might be, maybe on the results basis, better known. It's hard to tell. So I would definitely check out for ion trap as well. But in all these things, they typically tend to run a little bit slower than people think. So I think quantum simulators is going to be a thing regardless, just because it's 100% noise free, but with the limitations of smaller, quantum circuits and, smaller algorithms, those types of things. And I think that's how most experiments are run today are being simulated. So, but you can simulate and then also get good or even great results in certain areas like images, image analysis, those types of things. Yeah, so I think, with the IBM is basically double hex topology, circuit depth. So definitely know these things: circuit depth, circuit width. So like I said, if anybody finds a circuit, you can put it in the chat here if it'll let you upload it. But basically you have wires, and those wires correspond to a qubit. So qubit, and it's off by 1, like most things classical with programming. So the first qubit is Q0, and it goes across, and it's a time. So say if you have 4 qubits, 4 lines. Now, if you look at it, and there's a function on, I think it's the circuit composer, where it lets you see on a time basis, because time goes left to right. So it lets you see at this spot, the certain phase of this specific qubit is this, and this qubit is this, and that qubit is this, and the 4th qubit, which is Q3, is that at that specific time. And then you go the next layer deep, and it'll say at this, qubit 1, and so on and so forth for the next 3. So, yeah, I mean, you have to learn circuits, you have to learn gates, these things. I wouldn't say you have to memorize exactly the matrices of all the gates. So it's basically, there's a gentleman, his name is Seth Lloyd. So he's an MIT researcher, and he's been along with quantum for a while. And, publications, for I think over 6 years or something like that. And he says is basically, quantum computing, you'll get your advantages basically on linear algebra. So quantum computing uses linear algebra, quantum mechanics, and complex numbers. Now, your benefits are going to come from linear algebra, meaning, matrix multiplication, those types of things. But it doesn't necessarily mean that you have to know everything about linear algebra. You have to know the gates, so an X gate is called a NOT gate, and it's the same thing as the classical, version of that NOT gate. And I think all the other ones are different for quantum, but say there's another one, it's a C-NOT gate, so that's a 2-qubit gate. So you control 1 qubit, and then the other one you bit flip or perform C-NOT on it. And there's a Y gate, which is bit flip and phase flip. Those types of things, but it'll just seem easier, as you get to know, quantum gates, quantum code, circuits, algorithms. There's a feature on Qiskit, and you have to find the page under entanglement. There's multiple Bell states. So Bell state is basically the quickest way to get quantum entanglement. And you click on one, and it sends it straight to your your circuit composer in IBM, and then you click basically 2 more times, you click to run, and then you verify your quantum computer, and then you run. And there's your first quantum computing experiment. It's easy. Any other questions we have? And just, like with anything, like with Python, it's easy to give up. And, same thing with, quantum circuits. And now we're talking machine learning and, these types of platforms or libraries that, you just keep going and keep going to groups, keep hearing people talk about it. I can't tell you the number of lectures I've been a part of here, virtually, that you'll pick up on the tones of the voice and basically what exactly is important. Because I remember with Seth Loy is basically he'll be talking and he'll say something is like, yes, and then he'll just pause, right? And you kind of pick up, based on, what they emphasize. Any other kind of questions as far as like the platforms go? Have you tried to get on IBM, or have you looked at TensorFlow Quantum? There's, the TorchQuantum, like I said, is maybe a little bit more towards the researcher, like the data scientist that, basically wants to use TorchQuantum and then manipulate it to get something. There's an emerging couple papers, and it's B8EK is the first author's last name. They're called Scalable Quantum Convolutional Neural Nets, and it's on the TorchQuantum site. And basically it says you can use less qubits, and then you also use this other part of an additional, it's called a reverse fidelity train. And anyways, they could use a 3D image, like I think it was close to 32 by 32 by 32 voxels. So that's a volume pixel, basically. And it seems like it might be one of the more advanced at the time, as far as like I've done a 8-pixel, IBM QNN, and a 28 by 28 2D image on Penny Lane. But yeah, you can check that out. So the 2 papers are called SQCNN, and then the other one's SQCNN-3D, and the author's last name is BAEK. So they're up on TorchQuantum as far as like the papers that have developed their own models based off MIT's TorchQuantum. And then I see we got some other people coming in. Any other last questions? And then you can feel free to unmute, or you can do video. And then if not, you can put it into the chat. But, stick with it. And, the same thing with QML, deep learning was a huge thing to learn, very likely at the time, because the hardware didn't really break to the late 1990s and the early 2000s. And then there was an FDA approval for a cardiovascular deep learning based algorithm in 2017. And a lot of my medical papers, with deep learning are based in 2017. So just something I'll click and everybody's like, oh yeah, everybody has to do quantum. Or that's the way it's looking like heading. Awesome. So without anything else, like I said, feel free to, so links for beginners for sure. And any other last questions or comments? Then if not, this has been discussion 80, April 27th, 2023. Have a productive rest of the week and a good night. Take care, everybody. Bye.